So I think I cannot use my pen. I don't know why. Okay. So people studying today's class, I will briefly leave what we learned in the previous class. So actually, the previous class we learned about the brief architecture of GPU. So I explained that the GPU's architecture is very similar to the CMD architecture. So which means that GPU executes instructions like CMD, single instruction, multiple data. And then the architecture of the GPU is similar to the so as you can see, the GPU architecture is similar to this array processor. So which means the GPU has multiple processing engines, and then with the multiple processing engines, multiple data can be executed in parallel. So that is the how GPU execute instructions and how GPU execute multiple instructions. Okay. And then before starting, actually in this class we learned about some execution model of the GPU. You know? Yeah. And then we will learn about the architecture, the microarchitecture of the GPU, which means that the architecture of the streaming multiprocessor. So I hope you remember the terminology of the GPU. So actually, in the previous class, I explained its figure. So actually, please remember the terminology of the GPU architecture, right? So you need to remember the streaming multiprocessor. A streaming multiprocessor is like a core of a CPU, and then actually the streaming multiprocessor execute works. Okay, actually, so in a CPU architecture, CPU execute instructions, right? So instructions are fetched from the instruction cache, and then the fetched instruction is incubate instruction fetch queue, and then the instruction fetch queue. The instructions are decoded, and then decoded instructions are issued to the issue queue of execution engine. That's how CPU works. Actually, the GPU architecture it's developed from the CPU architecture, right? So the architecture is different, but GPUs are also general purpose GPU, so which means that GPUs need to execute the instructions. So the instructions are fetched from the instruction cache, like CPU, and then also GPU has the instruction fetch queue. But the differences in GPU is that the GPU execute work, okay? Because as I explained, work is a group of threads. Okay? GPU groups the multiple threads into a work. Actually, the work is the hardware unit, not a software execution model. Actually, the software execution model of the GPU is related to the software engineer. And so actually, the software engineer needs to organize GTA dimensions. So actually, so which means that software programmers need to know about the GTA. Also, in the GTA, there are multiple threads. So these thread execution models are also related to software engineers. But work is different. Work is the hardware unit. So actually, the work structure is not related to software engineers. So actually, this work is a hardware unit. So GPU actually execute words. Okay, it's similar to an instruction in CPU architecture. Actually, in a CPU architecture, CPU executes instructions every clock. So that so actually CPU can execute multiple instructions, right? But we assume that the CPUs can execute every instruction every clock. But GPUs can execute every verb. Okay. So verb is very similar to an instruction in a CPU, but no, in a verb there are multiple threads. So actually, NVIDIA GPU, I think it's the same to the AMD GPU. The little threads are grouped into a single verb. And then I explained that this verb share the same program counter. So which means actually these verbs in a single thread share the same instruction. So there are multiple threads, but these multiple threads execute the same instruction, which means that it's similar to the SIMD model. Okay, single instruction, multiple data. But so in this class we will learn about the GPU execution model. So GPU execution, and actually the GPU execution model is called SIMD. SIMD. The SIMD means like the single instruction multiple thread. Okay, like instead of D, the data, the SIMD execute the multiple thread. Okay, so which means that the SIMD architecture, actually the SIMD architecture is very similar to SIMD, but SIMD architecture has its own features. Okay, so this class we will learn about the unique execution model of GPUs like SIMD model. So I also do remember some terminology like the registers, then shared memory, data cache. But also, I hope you can remember the software hierarchy, the kernel hierarchy of GPU, such as the CTA, it's cooperative thread array, or the CTAs are also called thread blocks. Also, I hope you can understand the multiple threads in a CPU, a CTA. Ready? Okay, so that's what we learned in the previous class. GPU execution model. So that's how GPUs are connected to CPU. So if you see the it's not powerful, but okay. It's very small. So GPUs, and I explained that the GPUs are co-processors, not a main processor. So actually GPUs need to be connected to CPU, but this is a little bit old model. So actually recently the GPUs are directly connected to GPU because recently GPUs require high bandwidth between CPU. So that's why the CPU directly control data transfers between CPU, main memory, and GPU. But it's a little bit older model, but as you can see, but GPUs are also currently GPUs are still co-processors. Okay, so which means that the GPUs are connected via PCIe bus, right? So which means a processor, which main processor such as the CPU, needs to provide some data and then binary files to GPU. Yeah, it's PCI bus. So CPU is connected to system memory. Actually, every data is stored in the CPU computer system's main memory, and the CPU control the data movement between the memory and the co-processors. Okay, so this is the structure of the architecture of the GPU. So because the GPUs are connected to both the CPU has the host interface, so it handles the data transfers between CPU and GPU. And then also GPU has the dedicated hardware for graphics pipeline, for graphics applications. But in this course, we focus on the general purpose GPU architecture for general purpose processors. Okay, so we need to focus on the architecture for general purpose applications. So as you can see, the GPU has the multiple tuning multiprocessors like core, and then actually these multiple this streaming multiprocessor execute works like CPU execute instructions. So you can see some hierarchy here on the GPC that is kind of cluster. So actually multiple SMs can be grouped into a cluster like GPC, but this is important structure. So actually, we can focus on the streaming multiprocessor. Okay. So in the streaming multiprocessor, there are some memory hierarchy and then execution unit. And as you can see, the multiple streaming multiprocessors are connected via interconnection network. So actually, this is the NVIDIA paper. So actually, the GPUs are commodity processors, so which means that we don't know the exact structure of GPUs. We just estimate. But as you can see, the NVIDIA actually used this interconnection network. So actually, we don't know the detailed architecture of the interconnection network, but maybe it looks like the wait time network or some mesh type, not mesh type because the mesh type, the tiles are connected with some nodes, and each tiles are connected via mesh, like this rectangular interconnection network. But maybe this interconnection network are used for some different types, such as butterfly or some other interconnection network architecture. But as you can see, multiple SMs are connected, and then these multiple SMs are connected to partition L2. Okay, the partition L2 cache is connected to DRAM. So, and then which means that in this architecture, you can find 6 DRAM partitions, which means that there are 6 DRAM controllers. Okay, so DRAM controller, there are 6 channels. So 6 DRAM controllers are independently access the DRAM chips. Okay, so I also explained this. So this is the host interface of the actually computer system, the Intel computer system actually. So I just copied this figure from the Intel chipset diagram. So as you can see, recently so you can find some communication link between CPU and GPU here. So as you can see, GPUs are connected to CPU directly. But slow devices, IO devices are connected via this main board chip. Okay, so which means the peripherals in a computer systems are also connected via hierarchically. Okay. Okay. So this slide also explains how GPUs are connected to the CPU. work. So, yeah, right. The host controls the data transfer between GPU and host main memory. So, and then let's see how GPU execute software like the kernel. So actually, I frequently mention kernel. So it yes. So I said that GPUs are general purpose processors. So which means that we can say that GPU execute some code. So we can say that these are applications. But I said GPU execute kernels. Why? So actually, when you run the CUDA binary file, actually you can write the code with the CUDA-C, and then also you can compile your code with the MBCC compiler. Okay, and it's a CUDA compiler. But how do we execute this compiled binary file? Actually, compiled binary files are executed on CPU, right? Which means that the CPU executes the compiled CUDA-C file, so CUDA binary file. Then what will happen? Actually, CPU executes a CUDA file. So in the GPU execution model, GPU just executes its kernel part. So I said this parallelizable part. Understand? So if you write a code like in the CUDA-C, you can find this CUDA-C file has the main function like the normal C code. So actually, when the main function is executed, main function executes this serial code. So which means that actually in the main function, some statements has this serial part, and then these statements as a normal instructions are executed by CPU. Then this program can encounter kernel code. So in a normal C program, we also make many functions, right? So some instructions, some statements are executed on a main function. It's also a function, but we use also other sub functions, right? So we can use the main function. So if a function code is encountered in the main program, then a program jumps to the function, and then the codes inside of a function are executed. Okay. GPU has the similar model. So actually, GPU executes only this parallel kernel code. Okay. So if you see the CUDA-C code, then you can find that the CUDA-C code has also the main function. And the actually the serial codes are executed by CPU. And then if this code encounters the parallel kernel, the kernel, and this kernel looks like there is a kernel name, and then images of the kernel are declared, and then also this kernel has the argument like the normal function. Okay, then if kernel is executed, these kernel parts are transferred to the GPU memory, and then actually only these parts are executed by GPU. Okay, but then how the results can be used by this program? If the result, if GPU executes this kernel, the result can be stored in the GPU's main memory, which is this RAM. So the result of the GPU actually the kernel. Result of the GPU kernels are stored in the GPU's device memory. Okay, so this DRAM is located in the GPU kernel. Okay, so then the result is stored in the GPU memory. And then if these results are used by the GPU code with the serial code, then we need to also transfer this data to the GPU memory. Okay, and so also you can find some other serial code in the CPU side. Then QDAC also execute this serial code with the parallel kernels are encountered. Then these parts are only transferred to the GPU, and then GPU only execute this kernel. That's why I frequently mention kernel, not an application. So actually, CUDA application is that the CUDA applications include this parallelizable kernel. Actually, these parts, the kernels are only executed by GPU. Okay, then CPU code calls kernels like a function, like functions. Okay, it's very similar to a function code. So, okay, so actually, I will also explain the example kernel of the GPU. Okay, so firstly, we will focus on the structure of this kernel. Okay, just focus on this kernel. So if we see the dimensions, the structure of the CUDA kernel, then you can find that actually the kernel generates multiple threads. Okay? So, and then actually GPU executor is generated multiple threads. But you can think like this. Oh, this is the same code. And then actually the same code. And why do we use GPU? We use GPUs for parallel processing. So which means that in a processor, it's a parallel processing instead of. So these processors handle array data, which include multiple elements. And then these multiple elements can be executed concurrently by parallel processors like GPU. So you can say, oh, it's the same code, which means, oh, in the same code, we can generate the same instruction. And then this code handles the multiple elements. Oh, this is the single instruction multiple data model, right? But I said, CPU kernels generate multiple threads. What does that mean? In a CPU domain, multiple thread. What is a thread? Thread means an independent program code, right? So independent, actually, thread means an independent application. Okay? And the CPU executes these multiple thread independently. When the thread execution is changed, and we call it this is the context switch. Then CPU takes another thread, and then CPU executes the different instructions in the different thread. So we can think that if there are multiple threads, then we can expect that these multiple threads are executed independently, right? So it means is thread number 0 is independent from the thread number 1. So thread number 1 is independent from thread number 2. That's how we expect the thread executions of CPU domain, but it's different. So that's why. So sometimes the CPU's execution model is trick is a little bit tricky to understand, but in a single kernel, GPU execute multiple thread, and then these multiple thread actually share the same instruction, right? Because the kernel code is the same. So it's like even though multiple threads are generated, these multiple threads execute the same program code, right? Because it's generated from the same kernel, the same code. So which means even though multiple threads are generated, with multiple threads generate the same code, right? Same instruction. But the instruction execution order can be different because these are multiple threads. But we need to understand that in a GPU execution model, even though the multiple threads are generated, these are multiple threads execute the same code, same instruction strings, right? Then, how GPU works? In a single kernel, multiple threads, like the hundreds of threads, but even the thousands of threads can be generated from a single kernel. Then, GPU overnights these generated multiple threads. Then, GPU executes these multiple threads. So actually, but okay, this is the GPU hardware. So if we just think that this is the this is the kernel code, and then kernel code is kernel generate the multiple thread. Okay, so it's a thread, a thread. It means a seal in Korean. So there are multiple threads. So okay, let's execute the multiple thread on the GPU. How? If multiple threads are executed independently, how can we execute the multiple thread? So which means, there are multiple cores here, and then actually these multiple cores are similar to the CPU core. And then threads. Actually, single thread is mapped to it's a single core, and then the single core can execute this thread. We can expect this execution model, but the GPU architecture is a little bit different. GPU architecture has also the hierarchically organized. So as you can see, GPU has the SM, or GPU has the SP, the storing practice of what's called the CUDA core. So GPU has the multiple very large register files. Then I also explained that GPU executes the work, and the work is a group of threads. So which means actually in a software execution model, we can expect this execution model. So which means a single core is assigned to each thread, and then actually the single core has the register file, cache, the execution unit, and then single core can execute the single thread. This is the CPU execution model. For GPU architecture, it's a little bit different. Actually, we see the GPU architecture, so we can find that the GPU architecture does not have independently working cores. Okay, GPU GPU architecture is hierarchically organized. So which means when this kernel generate multiple threads, these multiple threads are also hierarchically organized, right? Because GPU has the hierarchical architecture. Right? same, the word, it is. So actually, when multiple threads are generated from a kernel first generates the thread blocks. Okay, and then inside of the thread blocks, and multiple threads are generated. So if you see the GPU kernel, then you can find that actually. So this is the kernel name. Then I also mentioned that these are kernel dimensions, and block and then PI. And then also there are some arguments. So these are inputs of kernel. But you can find some unique feature of the GPU kernel and block and T and TNE. So actually, these dimensions define the structure of this thread block and then structure of thread block. So which means even though a single kernel generates multiple threads, these generated multiple threads are also hierarchically organized. Like the first, the kernel generates multiple thread blocks, and then these thread blocks are also called CPAs. And then inside of this thread, the single thread block, multiple threads are generated. And then actually, actually, so as you can see, there are multiple SMs. Thread blocks are assigned to SMs. So which means that in a single kernel, this kernel generator. Let us split this kernel generator. 16, okay, 16 thread blocks. And these generated 16 thread blocks are assigned to SM. Like thread block 0 is assigned to SM number 0. And thread block number 1 is assigned to SM number 1. Something like that. Thread block number 2 is assigned to SM 2. Like this. And then think like this. I said SM is similar to a core. And then inside of a core, and then in the thread block, we can find many threads. Okay, but SM is the independent core, like it works like a independent CPU core. So it means actually the thread inside of the same thread block and share some hardware components inside of one SM. But how about the different thread blocks? So as you can see, so in this kernel, there are n thread blocks. You can find the thread block number 0 and thread block number 1. So the same thread block is assigned to an SM. And I mentioned that in an SM, threads can share some hardware components, but different thread block is assigned to different SM, which means that the thread inside of a thread block 0 cannot share the hardware component shared by the thread number 0 or the thread block 1. Do you understand? So like the multi-threading, so if core executes the multiple thread, then its multiple thread can share the audio component, such as the error cache, right? And then I said that the thread block includes the multiple thread, and then this thread block is assigned to the different SM. And then inside of SM, these multiple threads share the same SM hardware, right? So which means this threads are executing the same SM. These threads can share the same audio components, such as the error cache or also the shared memory. But the thread block, the different thread block is assigned to different SM. So actually, this thread block also generates the multiple thread, but these threads are assigned to a different SM, which means this thread cannot share the same hardware with this thread. Okay, that's why. So actually, GPU kernel has some features like the shared memory. Okay, so we will learn about the shared memory in the next classes. And then so also has some synchronization features. So actually, these features are shared only inside of a thread block. Okay. Even though these threads are generated from the same kernel, these thread in the thread block 0 and the thread in the thread block 1 cannot share the same shared memory. Also, the execution of these thread blocks are only can be synchronized by barrier, but these barrier synchronizations are only applied to threads inside of the same thread block. Okay, this is somewhat a unique feature of the GPU. So actually, this hierarchical structure of the GPU kernel is caused by also the hierarchical architecture of the GPU, like the SM and works. But because of this hierarchical architecture, then the thread block and the thread has some limitation, some restriction, such as the shared memory or stereo synchronization. Okay. So okay. So this is the unique feature of the GPU execution model. Then also, but you can also understand that in a single kernel, the thread blocks are generated by thread block dimensions, and block. Also, inside of the thread block, multiple threads are generated. And then this number of the organization of the multiple thread in a thread block is determined by thread block thread dimension. Okay, PID. Okay, and then so which means that the different thread blocks have the same thread organization. Okay, same thread dimensions. Then CPU needs to distinguish different thread block or different thread inside of the same thread block. So for this purpose, the CPU kernel is the block index, then thread index. So it's like the array index. So we can identify different thread block in the block index. So we can also organize the block index as the 1D or 2D or 3D dimension. Also, inside of a thread block, we can also identify the different thread with the thread index. Okay, So you can also organize the thread index in the 1D or 2D or 3D, like X, Y, Z, like this. So think like this. So GPUs are also actually originally designed for graphics processing. And then, the graphics processing has the X, Y coordinates. Also, we can generate some depth coordinate like the Z. So that's why the GPU has the 3D dimensions. So, and then the index of the thread blocks and then indexes of the threads are organized using the 3D thread indexes or 3D block indexes. So this is the example. So in this example, so there are multiple corners like corner 1 and corner 2. And then as you can see, in this corner number 1 generates the 4 thread blocks. Block 1, block 2, block 3, block 4. But we can identify the default blocks with the block index. So as you can see, these are the 2D block dimensions, like from 0, 0 to 1, 1. So we can identify block indexes like the 0, 0, 1, 0, 0, 1, 1, and then like X, Y. And then inside of this thread block, we can also organize the multiple thread like this. Like these thread indexes like 0, 0, 0, 1, X, Y, Z. So using the thread indexes and then block indexes, the GPUs can identify different thread. Okay. Then, so let's see the example of the vector addition. So vector is the multiple element, and then this vector addition is good for parallel processing. Is good for vector addition. So we can create the multiple elements from the vector. We can just perform addition for each element. Then, how can we write a code for this vector addition? So this is the example of the CPU code. So as you can see, this is the main function. And then firstly, we need to allocate the memory for the vector A, vector B, and vector C. Okay, and then this is the function. So inside of this function, I'll receive the pointers of vector A, vector A array, array A, array B, array C, right? So then this function is called by main function. And then inside of the main function, then how can we perform vector addition? We can perform vector addition like this. So this is the iterative for loop, and then this for loop is repeatedly execute the add instruction for the different elements of the vector, and then this element is indexed by index number array. Okay, we perform this add operation serially. Then, how can we exploit GPUs for parallel processing? So actually, the memory allocation is not shown in this slide, but we already know that for this vector addition, then we need to also allocate the GPU memory with the follow function, and then actually this function needs to point the address of this array, right? So actually, the vector, the GPU requires the similar operation, similar preparation. So actually, when the GPU kernel is executed, then you need to understand that actually the kernels are executed on GPU device, and then GPU device has its own memory hierarchy. So what does that mean? Even though Q.C code is executed on CPU side, the required data, like the array A, array B, array C, needs to be transferred to GPU memory because the kernels are executed on GPU. So, firstly, we need to allocate this space for the memory space for array A, B, C of the GPU side. So that's the memory allocation command on the CPU side. So we need to allocate device memory for A, B, C. And data. You know, the Q.C code is executed on the CPU side, so which means that actually the data is in CPU, right? See, actually, so CPU memory. But now to execute the GPU kernel, then GPU has its own memory hierarchy, so which means that GPU requires the data for executing kernel, which means we need to copy these required data to the GPU memory. But in this example, we just perform the vector A plus vector B, and the result is generated and stored in the C, the array C, and for the array C. So GPU requires A and B, so vector A and vector B. So we need to copy A and B to the GPU's device memory. So which means we need data transfers from CPU to GPU. Okay. When the GPU has the data, then the kernel, the vector and kernel is launched on the GPU side. Then GPU executes this kernel. And then GPU executes the vector addition, the result. The result will be stored in the GPU's device memory, right? GPU has the independent memory hierarchy. So, which means that when the C is generated, C is calculated. Where is the C? C is in the device memory, GPU's device memory. Then, in order to use the calculated data C on the CPU side, then also we need to transfer the result to the CPU memory. So we transfer also copy vector C data to the CPU memory. So we also require the data transfer from GPU to CPU. And firstly, we allocate this memory space of the device memory. So we need to put in the memory space of the GPU's device memory. That's how GPU execute the kernel. But as I mentioned, this Q.C is executed on the CPU side, so we require these processes. The data transfers, the kernel is launched on the GPU, and then also the results need to be transferred to the CPU memory. Okay. Okay, so okay, so yeah. Okay, so let's take a 10-minute break. Then I will continue explaining about the GPU kernel execution. Okay, any question? Okay, let's take a 10-minute break. Okay, let's resume the class. So I can type now. And sometimes we would start a problem. 저는 이제 뭐라 그럴까 터치 스크린하고 별로 안 써서 터치 스크린에 라이트 하는 거를 별로 안 좋아해서 그래도 좀 해야 되니까 윈도우즈 태블릿을 사서 어차피 나야 타이핑을 더 많이 하니까 윈도우즈 태블릿으로 하잖아요. 때문에 어쨌든 요새 태블릿이라든지 이런 것들 펜으로 막 쓰고 그렇게 하는 거를 태블릿 안드로이드가 맥이죠? 맥 OS라고 해야 되나? 아이패드 OS 이런 것들을 광고를 잘 해놨는데 윈도우즈는 좀 또 여러 번 let's resume the class. So we are learning about how the GPU kernels are executed, how the GPU kernels are organized the CPU side. Okay, because as I explained, even though we write the code, with CUDA, then what this CUDA binary is executed on the CPU side. Only the kernel, the parallelized kernel is executed on the GPU. So also you need to remember that GPU is a coprocessor. So which means that in order to use the GPU, then we need to transfer the data from CPU to GPU. That's the very heavy overhead of the coprocessor architecture and the coprocessor structure, because the data need to be moved to the other devices. So this is not a good model, but it is a requirement because we need to use the data to execute instructions. So that's why we need actually, and then GPU is the coprocessor. That's why we need to transfer data from CPU to GPU. Okay. So I also explained how the kernels use the GPU memory or the device memory. So actually, device code. So we can distinguish the kernels with the kernels and the main code of the CUDA-C as the device code and host code. So host means it's a CPU side actually, right? So and then as I mentioned, the GPUs are coprocessor. So which means that we frequently call this coprocessor is the device. So CPU is actually the host. It is the host system, but in order to accelerate the parallelizable code, it's called the kernel, and we use GPU device. So as I mentioned, even though the kernel generates the instruction, these instructions need to be transferred to the coprocessor, and then coprocessor execute these instructions and then data. So GPU is also general purpose processor, so which means that the GPU also has the register file and its own memory hierarchy. And how these registers and the memory hierarchy is accessed by GPU kernel. So as I mentioned, the kernel in a single kernel, this kernel generates the multiple CTA, CTA0, and CTA1, CTA2. And then inside of the CTA, these CTAs generate the multiple graph. And then I mentioned that when we think about the graphs, then actually we expect that threads are executed independently inside of the any process, actually, any processors. So, and then the GPU kernels are compiled, and the GPU kernels also generate multiple instructions. And then these instructions look like risk type instructions actually. And then, everyone knows that when instructions are executed, instructions use registers. Okay, that's why GPU also has very large registers to support multiple threads. So, because GPU generates the multiple thread, these registers are also assigned to a single thread. So, which means that instruction is generated, which means that the GPU instructions are compiled from the GPU kernel. Then, like the add R1, R2, and R3, we can find registers in the compiled GPU instruction. Then, these registers are independently used by each thread. Okay, so which means that registers are not shared. And that's obvious. We cannot share registers among multiple threads. In the CPU execution model, we cannot share register data. So actually, the registers are independently assigned to each thread, and then this register is not shared. But GPU has also global memory, and the GPU's device memory and DRAM. So we can also find the load instruction in our GPU, and then load instruction access this GPU device memory, and we can find that the device memory space is shared by multiple threads, right? Because if we see the architecture of the GPU, we can find that DRAMs are connected to multiple SMs via interconnection network, which means that the DRAM space can be shared by multiple SMs. It's the same to the L2. L2 partitions can be shared by multiple SMs. So which means that the L2 space can be shared by multiple threads. But registers cannot be shared. Okay. So GPUs use its own memory hierarchy. GPU kernels can use its own memory hierarchy, and then host CPU manages the launch of the GPU kernel, and then data transfers between GPU's host memory and GPU's device memories. Okay. So now to support this operation, CUDA supports some device memory management the device memory management functions. Okay, because it is a function. So first function is the CUDA malloc. Okay, so I believe you know about the malloc. It's a memory allocation function in a C. And then CUDA malloc means that the required memory space is allocated on the GPU's device memory. Okay, so CUDA malloc allocates the memory space of the GPU's device memory. So if you use the malloc, then you need to use the free, right? If the free just complete using the target memory spaces, then we need to free the allocation of the memory, right? So CUDA also supports the free function. It's called the CUDA free, which means that the allocated memory space is free from the device memory. And then for the data transfer, CUDA supports the CUDA mem copy. So this CUDA mem copy supports the data transfers between CPU's host memory and GPU's device memory. So for this mem copy, we need to identify the pointer to the destination and the pointer to the source, and then the number of bytes. So which means that the amount of data. So actually, the CUDA main copy it performs the direct memory access between the host memory to the GPU's device memory. So we require this information. So let's see the vector add example. So this is the vector add function. So we can find some other function for GPU's device memory management. So you can find the CUDA malloc here, and here. So if you see there's a CUDA malloc, then you can find this is the pointer, and then the side of the data is identified. So actually, it's very similar to the malloc function in a CPU side. So we also identify the pointer of the array, and we also identify the side of the data. For using malloc function. Also, actually, it's very similar, but you need to remember that when CUDA malloc is executed, then the memory space is allocated on the GPU's device memory, right? The GPU's device memory. And then, as you can see, you can find the CUDA mem copy. So in this example, underbar D represents the device memory. Then, and then this array represents the array of the host memory. Okay. So if we see the CUDA mem copy example, then you can find this is the destination. Okay. So device memory, the GPU side. And then this is the host memory space, and then side. And then this argument defines the direction of the memory copy. Okay, so also you can find the same, a similar mem copy function here. Then we also need to allocate the device memory of result T underbar D. Then kernel code is here. Kernel code will be here. Okay. And then after that, we need to create the device memory spaces. Okay. That's how we use the CUDA malloc, and then CUDA mem copy, and then CUDA free. Okay. And then next the vector add. So so this is the host code. And then this is the device code. So device code means that GPU executes the only device code. Okay, so this is the kernel of GPU execution. So if you see this device code, then you can find some directive like the global, then which means that this global means that the CPU launches the GPU kernel. Okay, and then you can find the kernel name here, like the function. So if you see that this kernel, then you can find, oh, this kernel is very similar to the function, right? Which means that actually the CPU launches the GPU kernel like a function, the CPU side. Okay. So we also require the argument, but as you can see, this argument is in the pointer to the GPU's device memory, right? So in the previous slide, we allocate the GPU memory space like A underbar D, and then the A underbar D, we just transfer the array A on the CPU side to the array underbar D. So it's the memory space A underbar D to the GPU's device memory. So if you see that this kernel code, kernel receives the pointer to the device memory space, like A underbar D, B underbar D, and C underbar D. Okay. Then you can find the index I, and then index I is calculated like this. Then the elements in a vector, so it's an array, is calculated like this. This is a vector addition, so actually these are vectors. The A and B are vectors, and then the index of the vector element is calculated like this. Okay? Only this code is executed. So what is different? Actually, the main operation is the same. So if we just compare the vector addition code with the for C, but it's a CPU. Okay, so the code is the same. So we can find that the element of a vector is accessed by index I. GPU code is the same, but as you can see, how can we calculate the index? Index is calculated from thread index and block indexes. Thread indexes and block indexes. Right. So in order to access the element of the array data, we require indexes, right? And in order to calculate the indexes for accessing array data, the indexes are calculated like using thread indexes and then block indexes. Okay? Understand? And then, so what does that mean? If this kernel is executed, then this I, if this kernel is executed on the GPU, this I is calculated from thread indexes, and then each thread has the block index like 0,0, and also you can find the this each thread has the thread indexes like 0,0,1, 0,0,0, 1,0,0, like this. And then we use these thread indexes and block indexes to identify threads. Okay. And then using this thread, we calculate the index of the vector data. And then this function is executed. So if we see that the CPU code, then we can know that even though the CPUs execute these add operations serially, but we can know that this add operation can be parallelized, right? So which means instead of using iterate loop, GPU just execute the add operation. Add operation. And then in order to fetch data from the large array, then we need to also calculate the index for the array. And these indexes are calculated from block indexes and thread indexes. Okay, so what is important? We cannot find any 4 iteration loop here. GPU just execute the index calculation and load instructions because we need to access the element of the vector data. So if we just this kernel is compiled, we can find some code for calculating I, and then some several load instructions like load for vector A and load for vector B, and then add instruction. So when this load instruction is executed, then load instruction stores the data to some registers like R1 or R2. Then we can find the add instruction like R3, R1, R2, and then we can find the store instruction. Okay, R3 to some destination. And that's it. So which means that the sequentially executed iteration loop is parallelized by GPU kernels. Then for this parallelization, we use the GPU's block indexes, and then word indexes. Okay. That's the device GPU, how the GPU device kernel is organized. So, which means even though the GPU kernel generates the multiple thread, then I already explained that multiple threads have independent register files. This multiple thread execute the same instruction here. So like for instruction for I, calculating I, then load, add, and then store some instruction. So these instructions are concurrently executed by multiple thread. Okay, it's how the GPU execute the multiple thread of the device, the GPU device. Okay, it's the GPU's execution model. And then if you see the host code, the host code just launch the GPU kernel. But we already learned that the host also needs to allocate memory space of the device memory, GPU's device memory. But when the kernel is executed, then actually the kernel is launched by host kernel. So as you can see, you can find the kernel here. And these are dimensions of kernel. Okay, so these dimensions besides the size of the number of thread inside of a thread, inside of a thread block, which means that in this dimension, each thread block includes the 256 thread. And then also we can calculate the number of thread blocks of this function. And then these are arguments. And then that's it. So when we write a GPU code, we write a GPU kernel, so which will be executed on the GPU side. Then host code just launch the GPU kernels, and that's it. Okay. So this is the completed version for calculating dimensions of thread block and then dimensions of thread inside of a thread block. Okay, and define the dimensions like this. So that we normally use the 3D dimensions, but as you can see, the Y and Z coordinates are 1, so it's not actually one only dimension. So kernels are executed on the GPU like this. Then, as you can see, you can find some options like the directives of the kernel declaration. So if we use the global, then which means that this function is kernel, but the GPU kernel is launched by host. But you can also use the device directives. The device directive means that it is launched by device code. Okay? but infrequently is the only instruction global. Okay. So, and then this slide shows how the CUDA code is compiled by and this is the compiler, the CUDA compiler. So no, the CUDA C code is very similar to the normal C code, but the only different part is the kernel part, which means also the device memory space is allocated on the GPU's device memory. So host code is compiled by normal C compiler, and then actually the CPU executes this host part, and the kernel part. And we already know that when the kernel is written, the kernel is generated. Then we define the kernel like this. Then only the kernel part is compiled by MVCC compiler, and then this MVCC compiler generates the device code. And device code, this device code is called the PTX code. You can find some document for this PTX instruction set. It's very similar to the Java bytecode, Java instruction actually. So the problem is that actually the NVIDIA changed their architecture, the GPU architecture, which means that actually each different generation have different architectures. So which means that the supported instructions can be changing. So MVCC compiler first generate the PTX code. So this is very similar to the Java instruction. So and then this PTX code is using the just-in-time compiler. This PTX code is also compiled, and then the device instructions are generated. Okay. And then the GPU just execute the generated instructions for each generation. Okay, so I explained about how the kernel codes are designed and how kernel codes are launched on the CPU side. And I will go to the next topic. Any questions before moving? Before moving to the next topic. No questions? Okay, so let's move on to the next topic. So now I will explain about the hardware architecture of the streaming multiprocessor. So I will briefly explain about the SM architecture. Then the next class I also cover the remaining hardware components of the SM, the streaming multiprocessor. So actually, so this is the so now I think you are familiar with this figure. Okay, so SM is similar to the core of the CPU. So actually, and then as I mentioned, the SM execute the works. SM execute execute works. Okay, so which like the instruction, the works are the execution of basic execution unit executed by SM. So if you see the detailed figure of the SM here. Actually, this is the formula picture. So you can find that, oh, this is the instruction cache, because which means that the instructions are fetched from the instruction cache. So, and the GPU kernel is compiled, and also GPU kernel generates the instructions, like the CPU instructions. And then these instructions are stored in the GPU's device memory. So which means that with the program counter, the instructions need to be fetched from the GPU's device memory. Okay. And each SM has its own instruction cache. It's I cache like the CPU. Then you can find the work here. The work schedule. So I said that GPU executes the multiple works, and then I also explained that the kernel is launched. Kernel launched the CTA, and then each CTA includes the multiple threads. Okay, and then the number of threads inside of a single CTA is determined by actually programmers. Okay? It is determined by block dimension. So it means that a single CTA may have 64 threads. Then some CTA from the different kernel may have the 32 threads, but also a single CTA may have the 100 threads. So that's because the number of threads inside of a single CTA is determined by a programmer. Actually, even though CTA is assigned to an SM, then these assigned CTAs may have different number of threads. So then how can GPU's SM execute these multiple threads? So if there are multiple independent cores, and then these independent cores have its own instruction cache, register file, and then data cache, and then like CPU, then we can also execute this different number of threads. But it's not efficient because we learned that single instruction multiple data assembly architecture is more efficient than normal CPU architecture when for the parallel processing, which means that with the single instruction multiple data can be executed. It's more efficient for parallel processing. But if the GPU executes the multiple thread like a CPU, then the efficiency may be very low. And then we already know that even though GPU learns the multiple thread, then these multiple threads are generated from the same kernel code. So it means that multiple threads can share the same instruction. So even though a single CTA may have different numbers of threads, GPU just group these multiple threads with the 32 threads, for example. Group the multiple threads into a work. And GPU execute these works. Okay, so multiple threads are actually executed concurrently by a work. So which means that if a single CTA has the 64 threads, then this CTA will generate the 2 works, right? The work size is the 32, and then it's 32, it will generate the 1 work only. And it's 100, then it will generate the 4 warps, right? 4 warps. 4 warps. So actually, in a single CPA, multiple warps can be generated. And then these number of warps are specified in the GPU hardware. So for example, the Fermi architecture, the single SM can launch on up to 48 warps. Okay. So there are multiple warps. Multiple warps are generated from a CPA. Then these warps need to be scheduled, issued to these cores, CUDA cores. And then I already explained that CUDA cores are just ALU. It is very similar to ALU of a CPU. And then there are multiple ALUs. And so if you see this figure, you can find that the Fermi architecture, how many cores? 16. So you can find the 16 cores here. And then another 60 cores here. This is the SP, the string multiprocessor, or CUDA cores. Also, you can find some 4 cores of the SFU. Then in this figure, you can find 2 warp schedulers. So actually, most of the instructions are like the integer or floating point instructions are executed by CUDA cores or streaming processors. And then load instruction and store instructions are handled by load store units. I will explain later. But most of arithmetic or logical instructions for computations are executed by CUDA cores. And then, there are 2 warp schedulers. So if you see this figure, so you can find that 2 warp schedulers can work concurrently, which means that in a single SM, 2 warps, up to 2 warps can be issued to the core. Well, these cores, the streaming processors. So in this figure, you can find that SM can execute up to 2 warps, which means 64 threads. Okay. In a single SM, this SM can execute 64 threads. Okay. But how? You can find but there are 60 cores here, there are 60 cores here, and then I already explained that a warp size is 32, which means that the 64 threads can be executed concurrently. So which means that it requires 64 cores or 64 SPs. Right. But we can find only 32 cores. Or 32 ALUs, CUDA cores actually. 32 CUDA cores. So, the execution unit, number of execution unit is the half of the number of threads. How? So actually, so this is the program picture. So actually, the clock frequency of this CUDA core is the double of the warp schedule. You understand? For example, this warp schedule works with the 7 MHz, but CUDA cores works with the 1.4 GHz, which means that using the clock, old clock, and these CUDA cores can execute 32 threads of the 700 MHz clock. Okay, so clock frequency is actually different for the program. So this is fast. So actually, the NVIDIA reduced the number of CUDA cores for executing a work. But okay, understand? So which means that if we see this figure of the SM, then we can know that some overall structure, overall architecture of an SM. Okay, this is the Fermi, and then if we see the Kepler architecture, so this is the next architecture of the Fermi. So you just okay. So if we just did this SM architecture, the SM structure, then we can find that. Oh, is it called the XM extended? So we can find 4 work schedulers. Okay, so which means in a Kepler architecture, a single SM can issue 4 works per clock. Okay. So we can find the very large register file here. Okay. Then I did not count the number of cores here, but I believe it's 6. I think this number is different, but I think the number of cores do not reflect the real number of cores here. But you can see, so you can find that the Fermi architecture includes the more cores, and then is Fermi the Kepler architecture. The Kepler architecture includes more cores, more CUDA cores. Then Kepler architecture can issue 4 works per clock. Okay, so actually the NVIDIA changed this SM architecture generation by generation. Okay, the Maxwell architecture. So actually, so if you see the next, so what is different? So you can find that the Kepler architecture can execute the multiple works, and then these multiple works can share the multiple processing units. Okay, so 4 works can be scheduled concurrently, and then these 4 works can share the many execution units. That is the Kepler architecture. But the next architecture is the Maxwell. The Maxwell architecture, you can find that, oh, this is called the SMN. And then inside of SMN, but it shares the same instruction cache, but we can find that work scheduler. The work scheduler is coupled to the independent, the separated cores. So which means that SMN, there are 4 work schedulers. So then these work schedulers can each schedule work. But if you see the schedule units to the cores, then we can find that the cores are tightly coupled to the work scheduler. So which means that this work scheduler can only use these cores. And then these work schedulers can only use these cores. So which means the execution units are separated. Okay? Sometimes they also we can find that register files are separated. So NVIDIA changes the architecture generation by generation. Okay? The next architecture is the Pascal. So you can find it's very similar to the Maxwell architecture. Okay. The full architecture, then you can find the NVIDIA is the tensor cores. Okay. And then also, as you can see, the NVIDIA also gives the different number of 30.64 cores and 30.32 cores. But the work schedulers are also coupled with the with execution units. Okay, so sometimes, so this is the summary of the different NVIDIA GPU architecture. So that's the program architecture. One, two, three, four, 15. So the Kepler architecture, the NVIDIA increased the number of cores inside of SF, also NVIDIA also increased the number of works. Okay. And then for the Maxwell architecture, even though the iCache is shared by multiple workspaces, so we can find that these execution units are separate, coupled with the workspaces, which means the execution units are separated. Okay. And okay, that's how the SM is organized by generation. Okay, so then let's dive into the detailed architecture of the SM, the GPU microarchitecture. So actually, so as I mentioned, the GPU is the commodity processor. So NVIDIA actually does not reveal GPU architecture to public. It's their secret. So we don't know the exact architecture of the GPU, but we can just estimate the architecture of the GPU from the some papers from NVIDIA. So some researchers from NVIDIA actually some researchers work in the academia field. They made a simulator, the cycle accurate simulator called the GPGPU sim. And then based on this GPGPU sim, we can also estimate the architecture of the NVIDIA GPU, because actually the GPGPU sim was developed by Toru Amod. He was an engineer of the NVIDIA, and now he's a professor at the University of British Columbia. Then actually he and his student developed the GPGPU sim based on the NVIDIA GPU architecture. So actually, based on this GPGPU sim, we can just estimate the GPU architecture. Okay, so the GPU architecture is not revealed to the public. And then also we can also find some academic papers. Okay. NVIDIA may publish some papers regarding the GPU architectures. Also, some people also publish the GPU architecture papers. Then based on the papers, we can learn about the GPU architecture. Okay. Actually, to say to the Intel CPU, we don't know the exact architecture of the Intel CPU. But you know, the history of the CPU architecture is local at the GPU architecture. So we just know the general architecture of the CPU. But we can just learn some architecture of the GPU based on this GPGPU simulator. Okay, and then also based on using the academic papers, we can estimate the architecture of the GPU. But the GPU implement the SIMT architecture. Okay, so we need to know about SIMT architecture. We learned about the thread hierarchy, like kernel, thread blocks, and the worms. Okay, and then as I mentioned, only this part. Structure of the thread blocks and then its own thread are related to the software part. Okay, and the software engineer just use this corner dimension, block dimension and the thread dimension in the thread block. Okay, and then inside of the GPU execute work. Okay? Then this work is actually called the waveform by NVIDIA, not AMD, waveform by AMD. But the thing, GPU hardware actually execute work inside of what SDM. Okay, so what is the work? Work thread within a single work share the same piece. So why GPU use work? Because GPU structure is similar to the CMD architecture as I explained. So, but GPU supports the CMD architecture. So CMD architecture is a little bit different from the CMD architecture, and then actually, to the software engineers, CMD architecture just provide some execution models like every thread executes the different execution path. So which means that to the software engineers, so they think that even though these multiple threads are generated from the single kernel, software engineers think that, these threads can be executed independently. That is the CMD architecture. But in the CMD, actually, it's a single instruction and multiple data. So the CMD architecture just handles the vector type data, and that's it. CMD is different. Programmers assume that threads execute the independent instructions. Okay, that is the CMD architecture. Okay, it's a little bit different. The CMD just to execute the vector type instruction, but CMD execute the multiple thread, then multiple independent thread. That is the software model. But not to support CMD, so actually, software engineers made it like the multi-core architecture. That's why the NVIDIA advertised that, our GPU has the hundreds of cores, and then number of cores in a GPU much larger than the GPU. That's why GPUs are better than CPU. They advertise like that. But if GPU has the multiple independent cores, then the size of a GPU is very large and very inefficient. So actually, the inside of the GPU hardware is the CMD. Okay, but in order to support the CMD, GPU supports the CMD-like front end. But the back end of the execution part is the CMD. But that's different. So not support the CMD-like backward like execution units. GPU has the work. Okay. So it's a little bit different. Okay. So I already explained this. Okay. So as I explained, the thread is now CTA is grouped into work, and work is executed. Okay. So then let's see what is warp. The warp includes the multiple thread. Okay, so it is warp, and then warp share the same PC. So same PC means that this is the like the thing like the vector add kernel, like load, add. So when I explain about the vector add, it's execute the load, add, and store instruction. What is the same piece? Same piece means that PC is pointing or this load instruction. Then same PC means there are multiple threads, and then these multiple threads execute the same load instructions. Okay, like the load, blah, 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 load. Then if the PC is pointing add instruction, then it's add. The same instruction. So actually this thread will execute the add R1, R2, R3. Also the thread is the same warp, they execute the add R1, R2, R2. Okay, so this is the warp. And then what is the Cindy? Cindy just execute the add B1, B2, B3 vector type data. So because the Cindy, each thread of the CT handles the scale register file. Programmers assume that this is the CT. Each thread can execute the scalar data. But the same instructions, so the same is the thread that share the same PC is grouped into one. Actually, the GPU execute is same instructions. They add R1, R2, R2. So what is the benefit? If this same operation, so which means that these same operations can be connected to the multiple processing engines. So that's why the number of CUDA cores is similar to the number of threads and warp. Okay, so this is called the CT lane. So which means that actually for this thread, XPR has this thread is connected to this processing engine. Okay, and then this thread is connected to this processing engine. So CPU just select the works from the multiple works, and then CPU execute this work. So scale the work to the execution engines. Okay. This is the CP engine. Okay, so we learned about the CP engine, then we briefly learned about how the work is generated from a kernel. Then actually, based on the work, the GPU execute the multiple thread. So I will stop here. Then the next class I will also cover some detailed architecture of the SN and how the GPU support the CT executions. Okay. So any questions? Okay, thank you for your attention. And see you in the next class. 감사합니다.